So I'm recording. So welcome again once more to all of you. And we are going to continue with our long journey on data analysis with R. And it's within the framework of activities of the R Club of the University of China to have every Wednesday sessions on various topics that can help one another, and it's for beginners, intermediate, and even experts, for everybody. And there will always be something to learn. So that's why it's always good to attend the sessions. Anyway, we are recording the session for those who have not been able to attend. So feel free to ask your questions. It will be a very short session, and I'll be more explicit to ensure that everybody understands what I'm doing. So for this session, we are going to look at the distribution to see whether the distribution is normal, skewed, or there is some kurtosis. And you know, these aspects are very, very important, determining whether we are going to carry a parametric analysis or a non-parametric test. So normally, before we carry a parametric test, we need to check the normality of the distribution, the skewness, and the kurtosis, of course. Even though those terms are a bit related, because when one is fulfilled, absolutely we can consider that the other is almost fulfilled. But sometimes some journals will want really to see the statistics for all of them in order to justify your analysis. But we are going to see some situations where we may not necessarily need to fulfill the assumption of normality, and we are able to carry out parametric tests. So for new commerce, I am Koh Pascal Dimbot, data analyst of the PyToka team, and also a member of the R Club. And I am going to tutor you for some time. Everybody, I hope everybody is comfortable, and we also have some others, R users and R experts that will come on sometime to also help and also tutor us so that we exchange and gain experience. Let me see, just a minute here. Okay, good. Okay. So for the normality test, the null hypothesis is that the distribution is normal. The distribution being normal means that the mean is 0 and the variance is 1. And when you have it graphically, you assume a bell shape meaning that most of the values are closer to the mean. And normally the measures of all the measures of central tendencies, median, mean, and mode, they are almost the same. They almost have the same value. So there are three main tests that you can carry out to check for normalities: the Shapiro test, the Jack-Bera test, and the Kolmogorov-Smirnov test. For the Jack-Bera test, you need the library T-series before you execute that test. I put them in order to show the importance of each of them. The Shapiro test is more performant, more efficient, and most of the time you go for the Shapiro test. That's the best test that you can use to check for normality. The Kolmogorov-Smirnov test is also good, but it's disadvantageous in the sense that if you have a sample size of less than 50, a sample size of less than 50, it will not be good to carry out the Kolmogorov-Smirnov test. And also when you have ties, what you call in French ex aequo in the values, it will not be good to carry out using the Kolmogorov test. And when do you know that the distribution is normal? Is when you carry out the test and discover that the p-value is greater than 0.05. So when the p-value is greater than 0.05, you can conclude that you have enough evidence that the distribution is normal. And you have to accept the null hypothesis, which says that the distribution is normal. When you visualize, another way of checking for normality is plotting the histograms. You can plot the histogram as you see here. You may also have this other shape. So this is the best shape that you can have. It's a perfect shape that shows normality. You see most of the distribution, most of the values, they are closer to the mean. You can also carry a density curve. That is, you plot a histogram and then you align to it the density curve. We are going to do it in R. You can also go for quantile plot using the QQ-num function in R. And then you have a kind of straight line distribution of point counts along the mean. So when the distribution of point counts is really along the mean line of the quantile plots, then you can also conclude that distribution is normal. And it's naturally, you cannot have a perfect normal distribution. So you always approximate. So you may not have this actual straight line curve as you are seeing here. Then some statistics that help us also to conclude about normality is what you call the skewness and kurtosis. What do we mean by skewness? Skewness is a measure of the asymmetry of the distribution, how asymmetric your distribution is. And your distribution could be symmetric, like here. It could be positively skewed, or you can also say right skewed, or it could be negatively skewed, that is left skewed. So these two cases, that is negative skewed and positive skewed, when you have such distribution, you can easily conclude that the distribution is not normal. So the best situation is when you have it symmetric. That is, the values are symmetrically distribution on both sides of the mean. And you see in this case, the mean, the median, and the mode, they are very different. Then you also have what you call kurtosis. Kurtosis is a measure of the thickness or the heaviness of the tail, as the tail of the distribution. Like you see this situation here, you may draw your distribution. You have a curve for your distribution, and you have this kind of a curve, and you say is this platykurtic in the sense that you are having a broad peak, as the peak is broad, and you have a light tail. The tail is light. You may also have leptokurtic, meaning that the thickness is very, very high, and then you have a kind of heavy tail. So the best situation is to have a mesokurtic curve. And the more positive value that you have for kurtosis, the more thickness you have for your curve. So when you do the kurtosis test, normally the best value that you should have for normality is 3, plus 3. Plus 3, that's the best, that's perfect normality. But they usually tolerate values between plus 2 and minus 2. Plus 2 and minus 2, so you have values among these limits. You can also conclude that there is a distribution is assumed to is approximately normal. So out of this range of minus 2 and plus 2, then you could say that this is not normal. Now the same thing with the skewness. If you do the analysis and you obtain the value of skewness, which is between plus 1 and minus 1, you can assume that your distribution is symmetric, that is not enough skewness. But if you have values that is beyond plus 1 or beyond minus 1, then your distribution is said to be skewed. When you have more and more negative value, that's their value is more and more negative, it means that it is negatively skewed, like here. And if you have the value which is more and more positive, it means it is positively skewed. So we are going to practice in R. I'm going to share the screen. R Studio. So everybody can see the screen. So you have the instruction script here. First of all, when you open your R, you clear your memory here. The memory of R is on the top right here. This is the tab here. So when you click on this brush, you click on yes, it helps to clear all the objects in the brain of R so that the computation can be done a little bit faster. You can also clear the command history here. You click on the tab and you click on the brush here, clear the command history. If you have something in the console here, that is the bottom left here, you can also clear it with this brush, or you click on Control L. And in your script, you have the title of your script. Like for our title today, we are going to check for normality, skewness, and kurtosis of some distribution. The next thing should be the required package. So if you need any package, you make sure you load those packages. Like for this case, we will need a package called moments that will help us to carry out the kurtosis analysis and the skewness analysis. So I'm going to load the package. There are many ways of loading. You can use library, the function library, or you can use the function require. Those are synonyms in R, in the language of R. Require and library, they are synonyms. And then we are going to use the package moments. So after writing the syntax, you click on run, or you click on Control Enter. So when I click on run, I've loaded the package. It's written somewhere here. The next thing is to load the data that we are going to use. So I have some data here, WDI. I'm going to share the data in the group so that you can also use it to practice. So how do you load it? You create an object. Let us see the object data. And since the data is in CSV, you are going to use the function read.csv, and in bracket now, you write since the working directory. And it's important to check the working directory so that you are very sure of what you are doing. So you can even use the function get working directory, Control Enter, and you will see here at the bottom left at my console, you see the working directory. That's the address where R is going to pick up the data. So it's going to go to my dist in a folder called R club. And within the folder R club, you have a subfolder called R club on line 2. And within the R club on line 2, you have another folder 12, 09, 20, 23. And we are actually here. We are in that folder here. And in that folder, you have this data WDI. So I'm writing just the name of that data, WDI. It's CSV, but since it is the values are comma separated, by default, it's comma separated. The separator is a comma, so I don't need to write again the argument separator. So I click on Control. Let us check. I've not loaded because there's a problem, okay? I need to add the extension CSV before I load. So if you look at the top right, you see the name of the object here has been created. You can see the object there. The next thing is to explore. Whenever you load your data, you do some basic exploration to see how the data look like. And one very important function is the function str. You write the name of the object, and that object is data. Increase the spacing here. You click here in front of the your line command 22. You click in front here and you run. When you run, you see at the console here, you have a data frame which has 1,560 observations. It's really a big data set, 1,560 observations, and 12 variables. You can even see here in the environment here. And you have two categorical variables. The rest are numeric variables, all of them. They are quantitative variables here, integers also. But I want us to take one of the variables to do the normality, kurtosis, and the skewness analysis. So we are going to take either imports or exports since they are numeric. So it's a data set on economic studies where they are trying to look at imports and exports between countries in monetary form. So here, sometimes you may need the names of the column. So use names function so that you have the names of the column. Why do you need it? Because sometimes it's important not to be typing. You can type and make error. So you just copy the name of the column and then you use here. So that's why I have these names here. You can do other basics exploration. We will not go into it now since that's not the essence of our topic of today. Subsequent classes, you can do more basic exploration. So we are choosing one of the variable to analyze, and let's take the variable import. For instance, it's numeric. You do normality test on numeric variables, numeric and continuous variable, in order what you call ratio scale variable. So those are variables that you have, the like height, the height of somebody, the weight, and so on. So those are quantitative continuous variable. So I'll be interested in getting for instance, the maximum value of imports. The maximum value, I use the max function, and you see, oh, it's much money, 2.8. It's in billions. So the values are very, very high. You see, plus E plus 12. It means times 10 to the power 12. You see, it's in billions. And if you check the minimum values too. What is the minimum amount of money there? Let us run minimum. The minimum is also very high. It's in billion. Yeah. So the first thing, we are going to visualize this distribution. And to visualize, you use the histogram, simple histogram, the function hist, and then you give the name of the variable. First of all, you write the name of the object, use the dollar operator, and then you write the name of that column, of that variable. And we are going to have our histogram that appears here at the bottom right. You can see the histogram here. Just looking at it, it's already telling something on the skewness, right? It's telling us that it is right skewed, but we can check that too. We can ameliorate this histogram since our essence is not data visualization, so we can ameliorate it and make it more beautiful with colors and so on. But that's not the essence of our topic. Let us add now a density curve to each. To add a density curve, you need to put, let me copy the line command, 35. I'll go here at 38. You simply add this argument, prop true. That's the first thing. It's going to change the scale here. You see, it's now density curve. You change the scale here, and there are very, very large values. That's why you are having e to the power minus 12. But to make it more aesthetic, it's sometimes good to reduce the scale. And then when we are labeling the axis, you can say now times 10 to the maybe to the 12. So we can even reduce the scale by dividing all of them. Let's say we divide all of them in by we are dividing the values, making it smaller. Since it's in billion, let's say we are dividing in by that's 1,000, 1 million, 1 billion. That's one. See, yeah, great. You see the values have been reduced here, but showing that we need to multiply each value by 10 to the power 9 to get the exact value. We can even reduce, let's see, let's reduce it and see. Not still good. Let us multiply 2, add more zeros. Yeah, it looks more aesthetic now. Okay, now let us add now the density curve. Use the function lines, and in bracket, you use another function density. And we are going to write all this. We're going to write the variable. Now we have here, we're writing the variable in bracket here. Source data. Okay, let us run. You can see the density curve on it, but it goes beyond. So we can extend the limits of the y-axis. We can even add the thickness so that it looks beautiful. So let's use the argument LWD and add the thickness, say, to 2, making it more thick. It is thicker now. Then let us add the limits so that we see the peak of the density curve. We can add the limits here. We'll add from here the line command 38 here. We are going to write y limit, and we're using the concatenation function from 0 to say let's say 0.06 and see the limits. Okay, you guys, you can see that we have added limits. Let us start again. We still need to add again. Let us write 8. We execute the first line command. The next one, we still need to add a bit. Let's say 10. I think 10 will go. We execute again. Execute. Yeah, it looks better now. And we can even change the color. You can use the color if you want it to look more beautiful. Let us use red. So I execute the 2-line code. You can see the color. You can even change the color of the bars, the histograms here, but that's not our essence now. Let's go to normality test. But when looking at the graph, visualizing it, we can only conclude that it will not be normal because it is right skewed. But let us also check using the Shapiro test, which I know is going to fail in the Shapiro test. Shapiro test data import. Yeah, the result is at the console. Let me show to you guys. See, the p-value is very, very small. It's very, very small, and it's telling us that it is very, very significant. So we reject the null hypothesis of normality, and we conclude that we have enough evidence that the distribution is not normal because p-value is far smaller than 0.05. Okay, and we can even do the other test, the kurtosis test. Simple kurtosis test data import. Execute the command. 31. You see, it's far beyond the limits, which are 3, which are +2 and -2. So the kurtosis is very, very high. Then what about the skewness? Skewness data import. We execute the line command. 4.6. The best skewness is 3, so it's already beyond 3. So it's really, really skewed. And since the value is positive, it is positively skewed as indicated in our graph. But don't panic when you have this situation and you want really to do a parametric test. For instance, you want to check how imports will vary with country. You want to check how imports will vary with country. Probably you want to do analysis of variance ANOVA and need to check the normality of your outcome variable, which is import. And when you are found in this situation, don't panic. There's solution. First of all, according to the central limit theorem, when the sample size is high, like what we are having here, 1,560, even from 100 already, it's already high. You can violate this assumption of normality. So normality is not so important now in statistics. Most of the time we used to say, no, if the distribution is not normal, we are not doing parametric tests. So there are some times that you don't assume it so much. You don't consider the normality test, and it is acceptable because what using justification is that your sample size was really, really high enough. That's why during research design, you should always make sure that your sample size is very high. When you have a sample size which is very high, it gives you more possibility, more room to select which type of analysis test you can do. But when you have a very small sample, you are also limited. So we have enough evidence to even do parametric tests because the sample size is very high. And according to the central limit theorem, the central limit theory simply says that when you have, if you want to get the means of several sampling, if many people do the same study and you have several means, you see that the means will have a kind of bell shape. It would tend to have a kind of a normal distribution because of the high sample size. But you can also do some transformation. What can you do? You can stabilize the variance of their distribution. Let us stabilize the variance of the distribution and see whether you can get something more better. You can stabilize it by log transforming your distribution. Let us log transform first in the graph and see there will be some changes. We are going to take the logarithm, the natural log here. In all this value, I'm taking the natural log. Natural log. Let us execute and see. Great. Are you guys seeing this? Let me add again. The limit 2 is equal to 2. Great. Don't you see that it's looking a bit like a bell shape after log transformation? We are making it to approximate to normality. It means that we need to do this transformation in our data. So if you also do it right here with a courtesy, I'm sure we'll also have something better. Courtesies after log transformation. Are we still going to have the 31, which is very high? Let us execute the command and see. 2.16. It has dropped drastically, and it is now within that range of 2 and then a +2 and -2. So the distribution is not so heavy tail now. It's not so light tail. It's not so peaked, and so on. That's what it means. So it's not so positively skewed as it was here. Let me go back to it. Positively skewed, but now after log transformation, I have something like this. So let's also check the skewness. 0.04. You see, it's within that limit of -1 and +1. So that's great. We have done this transformation, and we have now, we can do our parametric tests without any problem now. In subsequent sessions, we are going to have so many sessions where we are going to learn all these stuffs. And you have to do all those parametric, classical parametrics and modeling. So we have done some stabilization here. We did some stabilization. Let me just come back again to what was there so that they should appear where they are supposed to appear. Okay, let me go and paste them where they are supposed to appear here. Yeah. Then you have the courtesy. So we are through this session. Any question? I'm open to any question before we start the session. Yeah, is anybody with any question? Hello?
Hi.
Yeah.
Yes, sir. Actually, I've really followed up all what we have been doing, and we have decided within our data frame, we choose just one variable, imports. I believe choosing another variable in the place of imports, I believe, can we have the same results?
No.
Can we do similar if we choose another variable apart of imports?
Actually, what you choose, let me again write the names of all those variables. They are here. What if you choose depending on the objectives of your study? Your study may be to model the imports with respect to countries and to see probably which countries did a lot of imports, for instance. You would do the normality test only on imports, okay? But now, if you're interested on export, you also do the normality test for export to model it with respect to countries, for instance. And the normality test is only done on quantitative data, okay? Because qualitative data are already non-normally distributed, okay?
Yeah.
So these are all those variables.
Okay, noted.
Have I answered your question?
Yeah, perfectly, sir.
Okay, that's great. Any other question? Feel free.
No.
Please.
Yeah.
Maybe you will excuse me because I was having network problems.
Yeah, I
But
discovered it.
I never understand. Yeah, I did not understand I did not understand skewness and kurtosis.
Okay.
What's the objective of doing that again, please?
Okay. Let me go back to the PowerPoint. Okay.
Yes.
The PowerPoint where I was talking about all this. Okay. Let me check. Yeah. Okay. Actually, the skewness and kurtosis help to understand the distribution whether it is heavy-tailed or it is light-tailed or it has a lot of thickness. For instance, when you talk about kurtosis here, the best situation should be mesokurtic here. That is, the thickness is not so much, and the tail. And the kurtosis is very, very important because when it is heavy tail, it means that you have a lot of outliers. You have a lot of outliers. So it is the outliers that make it to be heavy tailed here. Heavy tailed here. And it will help you to understand the distribution and know what type of analysis you have to carry out. So if your distribution, if your data fulfill skewness and kurtosis, you can conclude that it is normally distributed because all these statistics help to tell the researcher whether distribution is symmetric or not symmetric. A symmetric distribution is a normally distributed division. So if, for instance, most of the values are at one end of the distribution, like here, we say it is positively skewed. Most of the distribution are here, and the mean, median, that is all those central, the measures of central tendencies, that's mean, median, mode, will be very different. The assumption for normality is that median and mean should be equal. Median and mean should be equal. So when it is positively skewed or right skewed, they are not equal. And if it is also left skewed, they are not also equal. So these tests are very important. They are very important because you have, let me remark here that there are some journals that will request these tests to understand really the distribution of their outcome variable. Okay? And you can always do some transformation so that you make your decision to approximate to normality. And you should know that they will never have a perfect normal distribution. And this is very, very difficult in nature to have perfect normal distribution. But there are some school of thoughts. There are some school of thoughts that brought some theory, the central limit theory, that which says that when you already have a very large sample, a very large sample size, when your sample size is very, very large, you may ignore normality and do parametric test. Even when you do the Shapiro test and it's not normal, you can still do the parametric test. So normality is not very, very important, but sometimes you may like to really fulfill it before you do the parametric test. Okay, very soon the session will end. So I thank everyone, and if there is any other question, you can always ask in our WhatsApp group. We'll always be ready to share our idea there. Okay, goodbye to everybody.
Bye. Thank you.
Bye. Thank you very much, Pascal.
Okay.
Bye. Thank you very much, Doctor.
Bye-bye. Bye-bye.